In this video, I'm going to work a simple truss example. I called it Easy Truss 1. What makes it easy is that the top chord is parallel to the bottom chord. And you'll see that here in a moment. So this is a 3-panel truss, 10 feet, 10 feet, and 10 feet. And it's repeating isosceles triangles, or equilateral triangles. And this is a 60-degree angle. There's a 2.4 kip load hanging at G. There's a 1.2 kip load hanging at F. So the entire truss is basically going to be bending downward under the influence of this load. And because of that, the bottom chord is going to be in tension. And all of these top chord and this member here are all going to be in compression. And then basically these members are going to alternate tension and compression. So you already have some insight into what you expect here. What we're looking for are the forces in DE and EF, in other words, in this member and this member. And we're also looking for the forces in CD, CF, and GF. So in CD, CF, and GF. This is a typical exam problem, or like an exam problem, because it's fairly common on an exam to give you a truss and then basically ask you for a couple members at one end that would require you to solve a joint at one end, and then ask you for one or two members in the middle of the truss somewhere that would suggest using the method of sections in the middle of the truss. And so this is really kind of an exam style problem, but a relatively easy one. So on an exam, the support reactions would be given, probably, but we'll go ahead and find the support reactions. Remember, because all of these loads are vertical and all of our supports are also vertical, and this is an equally spaced truss, 10 foot, 10 foot, 10 foot, you can write the moment equation to get the support reactions, but EY is basically equal to 2/3 of 1.2 and 1/3 of 2.4. And so if you write that out, you basically get EY is 1.6 kips here. And we'll just put that here, 1.6 kips. Okay, so that's EY. So the problem asks for the force in DE and EF, and that it won't tell you, the test problem won't tell you that, but basically it's asking you to solve this joint right here, the method of joints. And so what I do, you draw, and I've already got the free body diagram drawn here, but I'm going to show you how I do that, because there's a method to my madness. So if you basically look at joint E, so this is E, joint E, and I'll draw the joint, and I'll draw the support reaction, which is 1.6 kips. So remember, on a truss, all of the members are two-force members. So in other words, the forces are going to act along these members, either in tension or compression. And so when I draw a joint like this, what I'll do is I'll draw like a dashed line and a dashed line. And these two lines give me the direction. Of course, this line is 30 degrees. This is 30 degrees. And so FFE is going to act along this line. And so I can just label that FFE. And FDE is going to act on this line, FDE. But notice I haven't drawn these as arrows yet. All I've done is drawn these as dotted lines, knowing that these forces act along these lines. And so FDE is either going to pull on joint E, which would mean he's in tension, or he's going to push on joint E, which means he's in compression. But since the support reaction acts upward at E, in order for E to be at equilibrium in the vertical direction, FDE is going to have to push downward. And so I'll draw him pushing down. And basically that means I'm drawing him in compression because he's pushing on the pin. And of course, you already knew that this whole top section is big compression anyway, but this joint kind of proves it. Well, once you draw FDE properly to keep this guy in Y equilibrium, now we're going to draw FFE. And so E is going to have to be in equilibrium in the X direction. If I put some coordinate systems on here, this is X and this is Y. The horizontal component of FDE is pushing to the right. There is no horizontal component of this guy. So FFE is actually going to have to pull to the left so that his horizontal component is equal to his horizontal component. And that basically places FFE in tension because he's pulling on E. Can you see that? So that's typically how I do a joint. Again, I give the directions first, and then I intuit the two different directions and try to realize what direction they act. And usually you can tell. And if the force ends up pushing on the pin, then that means compression. And if force ends up pulling on the pin, that means tension. So if we go back to our actual free body, which is here, and that's exactly how I drew this guy. I drew it in pieces. Notice also I labeled the small angle. I didn't label this 60, I labeled the 30. It's usually easier to deal with smaller angles. And so a cosine of 30 is fairly straightforward. A sine of 30 is fairly straightforward. If you do the 60, then you go, well, this guy's really the sine of 60 and this guy's the cosine. It's just, to me, it's just easier to deal with the smaller angles. So once you draw the free body diagram, we can write two equations of equilibrium, usually a y summation and an x summation. So in the y direction, if we write the x equation first, there's actually two unknowns in the x equation. So this guy and this guy are two unknowns. So the x equation doesn't get me anything yet. And so I'm going to start with the y equation. And if I take up to be positive, I have 1.6 up minus FDE cosine 30 is equal to 0. And so FDE is 1.848 kip. And because it's pushing, he's compression. When I write the x equation, if I take to the left to be positive, I've got FEF minus the x component of this guy, which is FDE sine 30. And there is no x component of the 1.6. And so FEF is 0.924 kip. And of course, that's in tension because he's pulling. Questions at the joint. Okay? So the problem also asks us to find the forces in these three members. And this suggests a method of sections. So in method of sections, I basically just cut him through here. And I draw the free body diagram down here. And I'll do that separately as well and show you how I do that. So what I'll do is I'll start with the section, the piece that I can see. So I'll start with that triangle. This guy. And then I've got a line of action of the top guy. I've got a line of action of CF. And I have a line of action of this guy. I've got the 1.2 acting down, 1.2 acting down. I've got EY acting up, which is 1.6. So we basically already said that with this truss being loaded the way it is, the top is in compression. And so I could actually draw FCD pushing on D. So this is FCD, and pushing on D means I'm assuming compression. We already said that the bottom chord, because the truss is bending downward, the bottom chord is in tension. So I can convert this F, F, G to tension. And these are assumptions now. Once we write the equations, if these guys come out positive the way they are, then that means we assume them correctly. If for some reason they come up negative, then we go, oh, I guess I assumed it wrong, and then we know it acts in the opposite sense. But, so we're using our intuition right now. Finally, this guy here. Okay, this is I call this an easy truss. So one of the things that makes this truss easy is because this guy is the top chord is parallel to the bottom chord. When you draw this free body diagram, this guy and this guy are parallel. And so when you think about the y equation for this free body diagram, the only unknown, and this is FCF. The only unknown with a y component is FCF. And if this guy's 1.6, and this guy's 1.2, and this guy's horizontal, then basically the vertical component of FCF needs to act downward, so its vertical component plus 1.2 is equal to 1.6. And so by looking at that, or thinking in that way, I can draw him in compression, which means I draw him pushing on this joint, which is joint F. And because this is parallel and this is parallel, and this guy's the only guy with a y component, it's pretty easy to see that he has to be down to keep this guy in y equilibrium. Okay? And so once you draw that free body diagram, then I'll set that aside. So this is the free body diagram. Oh, let's do a few more things. Let's get some dimensions off of here, since we got the big picture. So this is 10 feet. This is 10 feet, because it's an equilateral triangle. This is 30 degrees. So 10 cosine 30 is 8.66. So this guy is 8.66 feet, because the cosine of 30 is 0.866, square root of 3 over 2. This is 5. This is 5. And at some point, we're actually going to sum moments up here at C. And so this is 5, and this is 5. Okay, so those are some additional dimensions that you need. So take a few minutes, get your dimensions, make sure they're right, and be sure to don't hurry that. Be sure you get it right. Okay, so that's the process of making the free body diagram and thinking about the directions of these forces. Once you have that free body, and please, don't draw forces on this picture. Draw a separate free body. One of the things you can actually do is you can actually bring an index card into the test and with nothing on it. And you can actually lay that index card right here. And especially on a complex truss, if you lay your index card here, this is your right-hand free body. And then this guy is in compression. This guy is in tension. And this guy is coming down this way. And so you can actually kind of get a free body without redrawing the whole thing like I did. And on a test, that could actually save you some time. And you can get these directions on it. So once you have this free body diagram, again, because this FCF is the only guy that has a vertical component, one of the first equations we can write is we can just sum forces in the y direction. And so we can say, take up to be positive, we have 1.6 minus 1.2 minus FCF cosine of 30 is equal to 0. And so FCF, the difference in these is 0.4. And so FCF is 0.4 divided by cosine 30, which is 0.462 kip. And it came out positive, so the way we assumed it was correct. And we drew it pushing, and so that's compression. So that's compression. If we started with an x equation, then we'd have 1, 2, 3 unknowns with x components. And so start with equations that will get you something. Our next equation will sum moments about f right here. If we sum moments about f, then you basically have 2 unknowns at f and just this one unknown up here. So if we sum moments about f, we basically have 2 terms in that equation. If I take clockwise to be positive, then I have FCD and his moment arm back to F is this 8.66 that we found, and that's positive. And then minus 1.6, and his moment arm back to F is 10. Minus 1.6 times 10. And so then FCD is 1.848 kip, and it came out positive, and so the way I drew it is correct. I drew it pushing, and so that's compression. FG, we're actually going to find this guy two different ways. So one way to find him, so we already know FCD, and we already know FCF. And so one way to get him is just to sum forces in the x direction, which we'll do. But another thing we can do is we can sum moments about C. And so we can basically slide FCD back along its line of action, and we can slide FCF back along his line of action. They intersect at C. And so if I sum moments about C, it basically removes these two forces from that summation. And all I'm left with is FFG, 1.2, and 1.6 in that moment about C. And so this is a really common method or technique on trusses where we slide forces along their line of actions in some moments about the points at which they intersect one another. So let me just show you what those equations look like. And so basically, if we sum forces in the x direction, which I think for most people that's probably a little easier, we basically have, so we have FCD, it's 1.848. So 1.848 plus FCF times sine of 30, and FCF, we found that to be 0.462. Right here. Minus FFG is equal to 0. There's no x component on this load. There's no x component here. There's no other load with x components. So I'm basically just using the x components of all three of these forces. And I get FFG is 2.08 kip in tension, the way I drew it. Another way to get FFG is, again, to sum moments about C. And at C, basically the line of action of these two forces intersect. And so the three terms in the moment equation about C is FFG, and his moment arm is 8.66, 1.2, and his moment arm is 5, and then 1.6, and his moment arm is 5, 5, 5. So his moment arm is 15 about C. And so if I take clockwise to be positive, I have 1.2 times 0.5 plus FFG, and his moment arm is 8.6, minus 1.6 times 15. And you can solve for FFG is 2.08 kip. And again, it's tension because it's pulling down here. So really two choices to get FFC. And of course, this gave us practice, to get FFG. And it gave us practice, again, writing a different moment equation. One of the interesting things about statics, if you like statics, it probably frustrates some of you who might hate statics, but on any given problem, there's not just only one way to work it. There's different ways to work it. And so on this section here, we showed you, three equations that you can write, but an alternate equation, an alternate moment equation. And there's actually probably a few other directions you could have taken too, but this is an approach here. So this is an easy truss. We got the two parallel chords. We only have the one unknown with the y component in the vertical direction. There are no zero force members on this guy, so we don't need to worry about that. So, and we did a joint and a section, which is typical on exam. They give you a truss, and to solve one or two problems, one or two answers involves a joint, and to solve for other things involves a section.